Toby. Merci pour l'introduction, Pascal. Bonjour, je m'appelle Toby Hocking et je suis californien d'origine, mais j'ai appris à parler français. Je vous invite de me poser des questions en français si vous préférez, mais je vais poursuivre ma présentation en anglais. So yeah, this is a talk that I prepared for the joint statistical meetings, which I will be attending in Toronto next month. And so this is a practice talk. The session is, I think, 20 minutes long, so it's going to be a quick talk. And so hopefully I can do a little practice and see if I can get it all done in time, and also maybe get a little bit of feedback from you guys to see if I can improve anything before the real deal. Before I start, since we have plenty of time, I thought I'd maybe give you a little bit of an introduction to our university. So let's see. I brought up this Northern Arizona University tab, but maybe we could just do an image search. So actually, our colleague Gabby here spent some time there last year, and I'm sure she will be able to tell you it's a nice campus in the middle of a pine forest right next to the mountains in Arizona. And surprisingly to maybe many Quebecers, we actually do get snow in Arizona. We actually had about like 4 or 5 months of snow on the top of the mountain here. Pretty good skiing. And so a lot of people come to Northern Arizona University for the outdoor activities, but I went there to be their professor of computer science, machine learning. So I'm pretty much the only guy who does machine learning over there. And yeah, so if you guys are interested to visit, or if you're in the area and you want to give a talk, please get in touch. More than happy to have you have it over for a talk in my lab, or you can just go for a hike in Grand Canyon or whatever. So I'll start the presentation now. So the title of the talk is Efficient Line Search Optimization of Penalty Functions in Supervised Changepoint Detection. And this is joint work with my student, Jaden Fowler, who we see in the picture here. He just graduated as a master's student, very talented guy. And so in my talk, I wonder if I need to move this so it doesn't interfere with the titles, Is that happening? Because you guys do see it on the screen, right? Yeah, okay. I don't know if that's going to work, but I'll try that. Oh, geez. Okay. So, yeah, in the first part of the talk, I'm going to be telling you about ROC curves, which are useful for evaluating supervised binary classification algorithms, which you probably are familiar with. So, in supervised binary classification, we're given pairs of inputs X with outputs Y, where the X vectors are typically P vectors of real numbers, and the outputs Y are typically coded as 0 or 1. And we want to learn a function f of X, which outputs a real number, and we predict a positive label Y equals 1 when f of X, a predicted score, is positive. So for example, in email spam filtering, X can be a bag of words vector where you have different elements of X representing the counts of different words, and Y can represent whether or not that email message is spam, and then you can train a machine learning spam classifier. Another example is an image classification, very popular. So here's an image from Jones et al. In PNAS 2009, where it explains how they use supervised binary classification for cell image classification. So they compute a bunch of features for each cell in a bunch of images, and then they show the images to trained biologists who's going to label them as, yes, this is the phenotype I'm looking for with this budding cell coming off, or no, this is not the phenotype I'm looking for, which doesn't have that phenotype. So using those labels, we're going to be able to train algorithms. So there's different algorithms for doing the binary classification, such as SVM, logistic regression, etc. And all of them are minimizing a differentiable surrogate of the 0-1 loss. And so that's the sum of false positives and false negatives. We're going to be talking about these two things. So let's define what they mean. False positives are when our predicted score is positive, but the label is actually negative. So in this example, we would be predicting the budding cell phenotype, but the cell is not actually budding. And the false negatives, this is what happens when our predicted score is negative, but the actual label is positive. So we're predicting that it's not budding, but it actually is budding. So both of these are not desirable. We want to minimize both of them. And there's sometimes a trade-off between the two. And people use these receiver operating characteristic curves or ROC curves to kind of get at this idea of, are we doing good for both the false positives and the false negatives? And so what this is I mean, I guess it's difficult to see now because I moved this thing. I don't know what I should do with this. Maybe like that. Oh, no, that doesn't work. Do you want to help me out here, Pascal?
I think you can. No. Oh, sorry. No. Oh no. Masquer le. Ah, d'accord. Ah.
Ok.
Ok. Puis je te laisse retrouver.
Ok, très bien.
Okay.
Okay, so we were talking about the ROC curves when Pascal was helping me. So thank you very much. So yeah, the ROC curves is a classical method from signal processing literature. And here I'm citing a textbook from 1970s. And so this has been used for a long time, like 50 years. People have been using this to evaluate binary classification. So what it is for a given set of predicted scores, we plot the true positive rate versus the false positive rate. And so each point on the ROC curve is a different threshold of the predicted scores. So when you take a look at these are 4 different potential ROC curves that you might be able to observe with different classifiers. And each time we're plotting the true positive rate versus the false positive rate. And we say the best classifier is this one on the left, which has a point in the upper left, right? So it's going straight up and then straight to the right. And it has an area under the curve or AUC value of 1. And so you can have a range of different models. Typically, it varies between here, which is the best, and here, which is the worst, but you can have some things in between. And typically, the way that people measure how good it is just by taking the area. So when you're looking at evaluating machine learning algorithms, we say, what is the best binary classifier? It's the one which has the highest AUC, right? On a test set or something like this, right? So the research question in this work is, can we learn a binary classification function f, which directly optimizes the ROC curve? So most algorithms involve minimizing the differentiable surrogate of a 0-1 loss, which is not the same objective, right? So minimizing the 0-1 loss can be different because there can be class imbalance, like lots of positive examples and maybe lots of negative examples, whereas, you know, with the true positive rates and false positive rates, we are kind of normalizing away the amount, the absolute quantity of the different examples in the two classes. So the area under the ROC curve is this AUC it's a piecewise constant function of the predicted values. So the gradient is 0 almost everywhere. So it cannot be used for learning directly with gradient descent algorithms. So you're probably familiar with training neural networks. We use gradient descent. You know, you use this backward method in Torch, and it's going to automatically compute your gradients. But if you're computing the AUC, all the gradients are going to be 0, so you can't learn anything. So how do we do this? So what we do in this talk, we propose a different objective. We propose to encourage the points to be in the upper left of the ROC space using a new loss function, which is a differentiable surrogate of the sum of the min of false positive and false negatives. And so that's what we're visualizing on this plot. So in this plot, we have the same 4 ROC curves. And so again, it's a plot of the true positive rate versus the false positive rate. But here I'm highlighting the points on the curves rather than the area under the curve. And so this is another way of quantifying how good the curve is, right? On this curve, we see that all the points are blue, which represents a minimum value of 0 between the false positive and false negative rates. So if you add up all of the values of all of these blue points, you get 0. So actually, this is another way of saying this is the best. It has a value of 0 when you add up all of those values. Whereas when you look at these other ones, you see that some of them are becoming red or different colors of, you know, light blue, light red. And what that represents is larger values for the minimum of these 2 error values, right? So what it means is that on these curves, you have some points on the curve which are starting to become suboptimal. And so we've changed the objective. We're not measuring the area under the curve anymore. We're measuring how far these points are from the ideal in the upper left. So that's the new idea that we propose. And I'm going to be talking to you about a second application of this that works for supervised change point algorithms. So let's talk about that next. So yeah, we have a question. We can stop. It's fine. Yeah. Sure.
Why do you have like this discrete type of feature? Like why the curves are not?
That's a good question. So the question is, why are these curves discrete and not continuous? Well, so that's an inherent property of finite data sets, right? So when you have a data set with n data points, you're going to have n points on the ROC curve. So it's maybe not obvious because usually the data sets that people do ROC analysis for have maybe thousands of data points. And so then the number of data points is greater than the number of pixels that you're using to display the ROC curve. So it's maybe not obvious that it's discrete, but the ROC curve is always discrete when you're working with finite data sets.
I was thinking that it was like a function of maybe the model parameter.
So the observation is you thought it was a function of the model parameters?
Yeah, just probably.
So the ROC curve, it's a function of the model parameters in the sense that it's a function of the predictions. For any set of predictions, you can compute the ROC curve. And for any set of predictions, it will always be a discrete ROC curve like this with a discrete number of points with discrete changes. Maybe there's going to be a lot of them, so maybe it seems continuous, but it actually is discrete, yeah.
So are you computing the sum of the minimum FPFM over all n points if you have n data?
That's right. Yeah, the question is, are we computing the sum of all of these minimum FPFN values over all the data points? And yeah, so it's not exactly true. It's over all the points of the ROC curve. There can be some cases where you have fewer points on the ROC curve than you have in data points, but yeah, in general.
Do we know how good it correlates with the AUC? Because I see the intuition. It's really straightforward, but I wonder if there are cases where
Indeed. Yeah. So we're going to be talking about this later. So the question is, when you minimize this, the sum of the min values, is it always going to result in maximizing the AUC or vice versa? And when you maximize the AUC, is it always going to result in minimizing the sum of the min values? Actually, it's true in the one sense and not in the other sense. And we'll talk about an example later. So it turns out when you minimize the sum of the min, this is going to encourage monotonic ROC curve like this. But in the case of change point detection, we have some weird cases where you maximize the AUC and you can get some strange situations where you're getting very large AUC values, but not very good values of this. Yeah. So actually, this is great. I was planning to do kind of a practice talk where I just run through everything in 20 minutes and like in the conference, they take questions at the end, but I prefer taking questions in the middle. So please stop me and take more questions. I like that better. So yeah, going on. So the session at JSM, it's about change point or time series data analysis. So we have also this application of ROC curves for supervised change point algorithms. So I'm going to explain about that. This is a subject that's not as well known as binary classification, but we can still use the ROC analysis. So you've maybe heard about unsupervised change point detection. So this is used in analysis of sequential data. So here we assume we have a data sequence Z1 to ZT, where T is the number of data points measured over time or space. And that would be the black dots in this figure, these figures below. So here's a plot of the data value Z, the Z value as a function of the data sequence and index, the subscript. And so, for example, these are data sets here in black that are DNA copy number data for cancer diagnosis that I was analyzing during my PhD 10 years ago now, more than 10 years ago now. And so one way to solve this problem or to detect the change points in these DNA copy number data is by doing this penalized change point problem. And so we go into details in this paper, Maidstone 2017, if you really want to know how we solve this problem. I'm not going to go into all the details here, but suffice it to say that this is a non-convex optimization problem where here we have a convex objective function, but a non-convex indicator function for the penalty, right? And so a priori, we don't use gradient descent algorithms because it's non-convex, but it turns out you can use dynamic programming to solve this very efficiently, log linear in the number of data points. So it can scale pretty much to whatever data set sizes that you want, and you can get the optimal solution for any given lambda. And so then you have this tuning parameter lambda, where larger penalty lambda values result in fewer changes like this. We only see one change, or 2 segments. And here, smaller penalty values, lambda, result in more changes. So you can have this lambda parameter that's kind of tweaking how many change points you get, and you probably want to choose some lambda which captures all of the real changes and not any of like the noisy changes that you see down here, right? And so how do we train this lambda parameter? So we proposed in 2013 at International Conference of Machine Learning to use weakly supervised change point detection. We're given a data sequence Z like before, these black dots, but we're also giving these label regions L, which I'm representing as this these colored rectangles here. And so inside of this colored rectangle, it's a label that means we want exactly 1 change point inside. So here we can say that it's correct because the model is predicting 1 change point. Here we say it's a false negative because the model predicts change points elsewhere, but it's flat inside of that region. So it's not detecting a change where there should be one. False negative. Here we see it's correct again, because again, we're predicting a change point where the label says there should be. And here we say this is a false positive because they're predicting 2 change points in this region where the label again says there should only be 1, right? So that's too many, false positive. So in this framework, we can do supervised learning by computing a feature vector X for every one of these data sequences. So here, this is just one data sequence, but we have a whole database of hundreds or thousands of them. And we get some feature vector, and then we can learn some function f of x, which predicts a negative log penalty value. And when you take a look at what that looks like, when you take a look at what the label errors function looks like as a function of that f of x, or the negative log penalty value, you see that it's similar to what we do in binary classification, where when we have very small values, when we have very small predicted values or predicted scores, we tend to have false negatives. When we have very large predicted values, predicted scores, we tend to have false positives. So we want to try to find some place in the middle where you could probably get 0 label errors, right? Or maximizing the AUC. So we can use these kind of curves to compute the AUC as well. The difference, though, is that in the case of binary classification, these curves are always monotonic. So the FP is always just going up, and the FN is always just going down. But here you can see in the case of change point detection, you can have these non-monotonic ROC curves. And so that's kind of an interesting observation that's going to lead into this comment here, where we can have these funny cases where minimizing the AUM or maximizing the AUC does not necessarily result in minimizing the minimum between the FP and FN. And yeah, just to say very briefly, we have these notations about an exact description of these curves, right? So it turns out in the context of the supervised change point detection, we know exactly for what penalty values we would be selecting a model with 2 or 3 or 4 segments, and we know exactly when that change happens. And so we can compute those values. And so it's these values where these error functions are changing that we're going to be using for learning in our learning algorithm. So I'm not going to go into how those values are computed, but suffice it to say, in our previous paper, we described how to do that. And it's easy linear time operation to compute those values to learn from. Any questions about that? Because that's a kind of non-standard thing. I've been doing this for about like 10 years, but I don't think there's a lot of other people who do this in machine learning. So, okay. So just to say, so using those weakly supervised labels in the change point data, we can use ROC analysis now, right? So because we have those labels, we can compute true positive rates and false positive rates. And here I have a figure that compares 3 different penalty learning methods. So those are 3 different f of x in the last figure. And so here, big penalty, constant penalty, or linear penalty, where here we're learning either 0, 1, or 2 parameters. So very simple kind of learning algorithms. In this case, unsupervised, and here very simple supervised approaches. And here we have 2 test folds on the 2 panels going from top to bottom. And in each case, we're plotting the ROC curves, and the different curves correspond to the different change point detection algorithms. Here, we're proposing, we had a previous paper in 2002, where we have this algorithm called labeled optimal partitioning, or LOPART in black. And we use this to demonstrate that the LOPART algorithm has consistently larger AUC values. So it's consistently more accurate than the previous baselines here, the optimal partitioning algorithm or binary segmentation heuristic. And so again, yeah, we use the ROC analysis in the context of change point detection, just like we do in binary classifications. At the end of the day, we can say which algorithm is more accurate. Right? So do we have any question about that? Okay. So yeah, so we propose next to do this complete line search algorithm for this new surrogate loss, the area under the min of FP and FM, which we call the AUM. So we've seen this first figure before. So we noticed before that a large AUC is correlated with a small value for the area under the minimum of FP and FM, or the AUM. And so again, we can see that in this figure. And so there I'm showing you another figure, which is the plot of the total error function. So again, these are the plots of the false positives in red and the false negatives in light blue, and also the minimum of those two, which is again the quantity that we're trying to minimize when we take a look at the color dots in this figure, right? So here we can see in the best case, the FN goes down right away, and then the FP goes up afterwards, which gives us a min function, which is just 0 everywhere. And the area under this minimum function is going to be 0. So in a slightly worse case, the FN function doesn't go down quite all the way, and then the FP function starts to come up. So then the min function here between the two is going up a little bit, and you have a small value for the area under the min. And in the worst case, here we have, pretty much the FP starts going up first, and then the FN goes down afterwards. And so you have a very large value for this area under the minimum of the FP and FN. And so this technique was previously described in our papers here in TransAI in 22 and in Journal of Machine Learning Research in 23. And so in this new talk, this new work that we're working on right now, we're proposing how to track how these thresholds on this plot change as a function of the step size in gradient descent. So we're going to use gradient descent to try to optimize this area under the min. And it turns out that when we take every step in gradient descent, if we keep track of everything very properly, and in particular how these thresholds here, when the FP and the FN are changing, if we keep track of those guys, we can get an efficient algorithm to do an exact line search or a complete line search. Do you have any question about this figure before we go on? So yeah, it turns out that, yeah, before I go on, maybe make a comment about this plot versus this plot. So in this plot, we were looking at the sum of the min values over every one of the points. And here we're looking at the sum of the area under these functions. And so it turns out that every one of the points on the ROC curve corresponds to an interval of values on this curve. And yeah, so it turns out that if we want to try to minimize this quantity, the min of the FP and the FN, and then just the sum of these values over all the points, it turns out that's a non-convex objective. But when we relax that to the area, that becomes an L1 relaxation. So it becomes not necessarily always convex, but continuous relaxation. So it's going to give us gradients. And so we can learn based on this quantity, but not based on the sum quantity. So again, that's like, this is like the L0 objective and the L1 objective if you've studied the L1 regularization technique. Any question? Okay, let's go on. So, so yeah, the proposed line search algorithm that we're working on uses the structure of the AUC and the AUM function. So we have a theorem that when you're learning a linear model, we have AUC, which is a piecewise constant function, and AUM is a piecewise linear function of the step size in gradient descent. And so why is that useful? Well, we can take a look at an example. Well, if usually when we're doing some kind of a gradient descent, I don't know if you guys use Torch, or I don't know, maybe you code the gradient descent yourself. I've done that a few times. But there's a choice of step size, right? Some people take constant step size. Some people do a line search. Anybody know what a line search is? Yeah, we know what a line search is. Line search is when at every step you're asking the question, what is the best step that I could take, right? So typically to do the line search, you can just evaluate a few points on a grid. Like what if I do 0.1, 0.01, 0.5? What's the best of those two values? And so here, this is what that would look like, right? So here we just took 4 values, 0.1, 0.2, 0.3, 0.4. That's a line search, right? It's a very simple line search. We're just searching over 4 values, take the one which has the best value. Here it looks like 0.2, right? But so it turns out if you take a look at what the line search looks like with this objective function, and you look at a lot more values, you see this piecewise linear structure, right? So here in this plot, instead of evaluating just 4 values of step size, here I evaluate for, I don't know, 20 or 30 different values. And so you can see very clearly that on the one hand, the AUC is a piecewise constant function of the step size. And the AUM is a piecewise linear function of the step size, right? So what that means is that there's these breakpoints in where you have changes in slope of the AUM and you have changes of values of the AUC. And so the main idea of our new algorithm is to try to detect where these breakpoints are happening. So then we can follow kind of the path of wherever the slope is changing and get down to find a minimum of this AUM value efficiently. Right. And what the intuition, why would that be efficient? Well, here instead of evaluating 20 points, you could only evaluate, I don't know, 3 or 4 points to get to the bottom, right? So do we have any questions about that? Or what is a line search?
Can you comment on why is it piecewise linear and the other one?
Yeah, that's a good question. So why is the AUC piecewise constant and why is the AUM piecewise linear? Is that right? So I don't know how to answer that without some kind of circuitous argument, but it's just kind of an inherent property of the AUC. The AUC, it's just like the 0-1 loss, it's piecewise constant. It's just got these discrete changes. Past which certain values you start to be good, right? So with the AUM, the reason why it's piecewise linear is because it's an L1 relaxation of this other objective, right? So as soon as we start looking at the area rather than kind of the sum of values, we're talking about an L1 objective, and L1 objectives are typically piecewise linear. I don't know if that answered your question, but.
Yeah.
And why is it better to do piecewise line search instead of constant step size?
Yeah, that's a good question. So the question is, why would it be better to do a line search rather than just using some constant step size? And it depends on your problem. I'm sure constant step size works just fine in a lot of cases. And actually, yeah, it does. If you get the right step size, it's great. Yeah.
Would you see that this question that what is happening is that like when you have a discrete domain for variables, then you relax it to like interval domain. Like what happens with the objective function on those variables is that it becomes piecewise linear because there is values between the discrete values that the actual variable can take. Maybe that is because maybe that's why the AUM is piecewise linear and the other is piecewise constant.
Maybe. I don't think I really understood your comment though. Maybe you could rephrase that and simplify it somehow.
I'm not in machine learning, but I'm working with discrete variables sometimes. And what happens is when we are doing a linear program on those variables, we relax the constraint that they are integer variables to real values, and they are between intervals.
Yeah, absolutely. Yeah. So yeah, so the comment is about kind of the L1 relaxation
Excusez-moi, on n'a plus le son. Est-ce que vous m'entendez?
Back. Comme ça, est-ce que vous nous entendez mieux?
Oui, le son est de retour maintenant. Merci.
Donc, ouais, peut-être que le son ne sera pas aussi bon, mais le micro devrait rester en vie. Donc,
Ok.
c'est le micro de mon ordinateur. Donc, on va essayer de remettre, masquer les commandes ici.
Ok, très bien, merci.
Hop. Voilà.
Okay, so like I was saying, it turns out that finding the breakpoints in these AUM and AUC functions, it turns out it's the same thing as finding the crossing points or the intersection points of these linear functions, these threshold functions. So in the first iteration of our algorithm, you can think about we start at these values, and then at the second iteration, what happens? We find that first intersection point, and what happens? We know that in this first interval, the AUM is evolving with some kind of constant slope, and the AUC is evolving with some constant value. Afterwards, what happens is we know now what is the new slope, and we also know what is the new value of the AUC, as well as the intermediate value. There's actually a different value that's exactly at that breakpoint than it is afterwards. And so basically what the algorithm is doing is at every point, we're saying, okay, what is the next intersection point that is going to be happening? And after we explore that new intersection point, what happens? Well, we get the new slope and the new AUC values. We also get some new possible intersection points that we could explore. And so kind of the trick of the algorithm is to efficiently compute these intersection points and store them in some efficient data structure. We'll discuss that on the next slide. But basically, we just keep going. And so that's the fourth iteration of the algorithm, fifth iteration of the algorithm. And so there's a couple of variants that we propose. One of them is called this first min variant. And here, after doing 5 iterations, we've come to our first minimum. So that means the AOM is starting to increase. So here, let's just stop. That's a good enough line search for now, right? Another variant that we propose is this linear variant where we do 6 iterations. Why 6 iterations? Because there's actually 6 lines or 6 data points. So we just do the same number of iterations as the number of data points, and we have a guarantee that we have an efficient algorithm. Why are we interested in that? Well, because we like linear time algorithms that can scale to data sets of any size, right? And in fact, because there's n data points, there's n squared possible intersections. So if you keep going to the end, you can compute the full path of AUM values and AUC values up to any step size, actually. And we call that the quadratic version because there's a quadratic number of intersection points in the general case. So that could be very slow. So do we have any question about how that works? So at the end of the algorithm, depending on how far you go, you've got at least, some part of the AUM and AUC functions, which are known completely. So we know for all step sizes in the gray region, we know what all of the AUC and AUM values are. That's pretty cool, right? Yeah. And it's much less work than doing the grid search sometimes, right? So the grid search here, we did lots of points evaluated, lots of wasted time. So here we only have evaluated a few things. If we keep track of the math correctly, you know, all the equations are going to be in our paper, but you know, yeah. So talk a little bit about the complexity analysis of the proposed algorithm. So for n labeled observations, we input n threshold, line, slope, intercept values. So those are the slopes and intercepts of the red lines on the previous figure. So then we compute all the possible next intersection points by storing them in a C++ STL map. Have you guys ever used that C++ STL? Yeah, it's pretty cool, right? It gives you all those standard data structures that you learned in your data structures class, but you don't have to code it yourself, and you know it actually doesn't have any bugs. It's great. So the STL map, it's actually a red-black tree. And so all the entries are going to be sorted by step size. So when we're taking a look here about what is the next intersection point to explore, it's a constant time lookup of which one is the next one because of the red-black tree. So it's a log time insertion. So whenever you find a new one, you have to insert the new possible candidates. That only takes a log time, so that's very fast as well. And so it's worst case linear space. So you might think it's worst case quadratic space because there's a quadratic time number of intersections, but actually we don't compute them all right away. We only compute the kind of adjacent ones, right? So here, these are the only two that could possibly be the first step size, after which, you know, there may be some other ones that appear later. So the space is always very reasonable. So yeah, we're going to talk about comparing a few different versions of gradient descent here. Grid, it's going to represent standard grid search where there's G, the number of grid points. And so this is going to be a G n log n algorithm. And here we have the three variants that we discussed on the last slide. So linear, where we only do the first n iterations. So this is going to be guaranteed log linear time algorithm. It's going to choose relatively small step sizes. And it's therefore going to use a relatively large number of steps overall in the gradient descent. So it's maybe not necessarily going, even though it has this guarantee of each iteration being fast, maybe the whole gradient descent is not actually that fast because the small step sizes, right? So in the quadratic version, we're going to do all n squared iterations. So this is n squared log n, so potentially very slow for large n, quadratic time. But again, we're going to be taking large step sizes, so small number of steps. Maybe it's if you take only a few steps, maybe it's actually pretty fast. And the first min version, we keep iterating until the first increase in the AUM. So it's the same as quadratic in the worst case, but it may be faster on average. And on the last slide, it was actually faster than both the quadratic and the linear one, right? So we saw how here the first min actually occurred before we did either a linear or a quadratic number of iterations, right? So in our empirical results, we have first a figure from our previous paper in Journal of Machine Learning Research, published earlier this year. We showed that AUM gradient descent results in increased train AUC for a real change point problem. So here on the figure on the left, we show what the AUC and the AUM and the label error function looks like as a function of the number of iterations in the gradient descent algorithm. So the gradient descent algorithm is minimizing the AUM, so obviously that's going to be going down. We see that when it goes down, the AUC tends to go up, kind of unexpectedly in the context of this change point problem. Label errors are going up, right? It's kind of unusual. In binary classification, we expect if the AUC is going up, the label errors would go down, right? But in the context of change point detection, what we did is we did an initialization to a point with minimal label errors already. So it's normal that since it's minimal already, the only place it can go is up. So what this shows is that in change point detection, there's kind of this trade-off between maybe minimizing label error and maximizing the AUC, and it's a kind of a trade-off that doesn't exist in binary classification. In binary classification, you maximize the AUC, you're obviously going to get a better model in terms of label errors too. But to give you an idea about the what the raw curves look like before and after optimization with the AUM. So the initialization looks like this. In the change point problem, you get this kind of funny non-monotonic raw curve in red when you just minimize the label errors. And that's because it's just trying to find one point which is very close to the upper left, basically. Whereas when you're doing the AUM optimization, it's kind of trying to optimize all of the points on the raw curve. And so you get a raw curve, which is kind of more monotonic and with maybe a little bit larger area, not necessarily with a better label error, right? So the best point here on the blue raw curve after optimization is here, whereas the best curve, the best point on the red curve before optimization was actually much closer to the ideal, right? So, here we showed that minimizing the AUM results in maximizing the AUC. And so in our new work, we analyzed the proposed line search algorithms. And here is one change point problem that I took from this UCI machine learning repository ChipSeq dataset that we submitted a few years back. And we did fourfold cross-validation in each one of the datasets. And we initialized a linear model by minimizing a regularized convex loss. So it's a surrogate for the label area that we previously described. And then we keep doing the AUM rate gradient descent steps with line search until the subtrain loss stops decreasing, right? So we do an internal subtrain validation split to tune the hyperparameters and the number of iterations of gradient descent, right? And so yeah, when you compare the 4 different methods, we can see that this first min proposed method on top is consistently a little bit faster than the grid search, right? So in all 4 of the test folds, we see that it's kind of getting the fastest computation time. After that, we see actually the quadratic and the linear methods in this particular data set are a little bit slower than the regular grid search. But kind of surprisingly, the linear method is a little bit slower than the quadratic method, right? You would think that the quadratic method may be slow because of that worst case quadratic time complexity, but it turns out that because the step sizes it takes are very big and the step sizes that the linear method takes are very small, you have to take so many more steps that it's actually slower. So that's kind of an interesting observation. And afterwards, we also look at the accuracy. So here's the same exact different methods, but here with different methods for line search, and here the max validation AUC rather than the computation time. And so what we see is that here the initialization has a relatively low value for the validation AUC, whereas all of the optimization methods are more or less have the same big increase in AUC, right? So some slight variations, like here the quadratic is a little bit bigger, but mostly we just see a big increase. They're mostly getting more or less the same kind of accuracy kind of a model.
Does it tend to overfit if you compare to the train AUC?
The question is, does it
If
tend?
you compare the train AUC, do you have I don't know, the train AUC is close to 1, or is it similar to what we observed here?
Okay, so question is, is there a difference between the validation AUC and the subtrain AUC? I would think probably no. I don't know. We'd have to look at the figures. But just like with any algorithm, you can avoid overfitting in the same way, right? You just you can choose the step size or choose the number of steps to do early stopping regularization or do whatever kind of regularization you want, right? Here we're doing early stopping, right?
The plots that you were showing, were they valid or from?
The plots that I was showing here, is that the one you mean? So this was just on the train set, I think. So, yeah. So this is so we can show that minimizing the EUM on the train set results maximizing AUC on the train set.
Do you have any? I guess that's a question, but for generalization, what does this imply?
Yeah. So here we look at the validation numbers, right? So here we show that using the different kinds of line search methods, we can get similar validation AUC numbers.
And you just mentioned that you are doing early stepping here.
Yeah.
So you keep a part of the training hold to perform early stepping.
Yeah. The observation is we keep a part of the train data to do early stopping regularization. Yeah. So we do the train test split and then we do a subtrain validation split with the train set. Yeah. And yeah, the variation that we see in these error bars here is over the random initializations, right? So it turns out, I mean, since it's it can be non-convex, the initialization can change the results. So you see some small variation there in this particular data set. And again, here we saw that it's a little bit faster. Maybe it's not going to be always faster, but at least we see in some data sets it is interesting to use the line search rather than a grid search. So let's end here. So the area under the rock curve, or the AUC here, is used to evaluate binding classification and change point detection algorithms. We have this paper with my student John Hillman in Journal of Machine Learning Research earlier this year, 23, where we propose this AUM, area under the min of FP and FN. It's the new differential surrogate loss for AUC optimization. So in this talk, we propose a new gradient descent algorithm, 3 different variants with efficient complete line search for optimizing the AUC, M and the AUC. And the empirical results that we discussed provide evidence that the proposed complete line search is consistently faster than the grid search, at least on the data set that we were looking at there. And it has comparable accuracy in terms of max validation AUC. And so here we have implementations available in R, C++, and Python. So in our R package, we have an implementation of the line search with the C++ standard template library. And in Torch, we have an implementation of the AUM loss without the line search, but at least you can compute the AUM if you want in Torch. So for future work, we're thinking about doing nonlinear learning algorithms that use AUM minimization as a surrogate for AUC maximization. For example, if you use the ReLU activation in a neural network, you get this piecewise linear structure for the line search as well. So that might be something that would be worth exploring. Okay, so I'll stop there. Thank you again, my co-author, Jaden Fowler, who helped me with the coding on this project. And I can take any final questions.
So this is for like a batch mode gradient descent, right? Not for distributed.
Right. So the question is, we use this for batch mode gradient descent, not for stochastic gradient descent. So when you say stochastic gradient descent, you mean like one example at a time, right?
It could be you could have mini batch.
Yeah, so this works just fine for mini batches as long as there's at least one positive and one negative example in the mini batch, right? But you can't do it with one example in the mini batch because then the area under the min is always going to be 0 and your gradient's always going to be 0.
Okay.
I don't know if that's obvious, but that's true. Yeah. Yeah.
Like, did you try it on like large scale?
Yeah, we did. So the question is, did we try it on some kind of large scale image classification data sets? And yeah, if you look at our GMLR paper, there are some results about that. Not with the new line search, but with the this torch implementation that we were talking about.
Do you have an idea if this would work with something like speech recognition?
Yeah, so the question is, do you have an idea if this would work in speech recognition and audio data? And I mean, it's like anything in statistics. Maybe it works in some data, maybe it works in some other data. Not everything is going to work well for everything, right? So but yeah, what I can say is that if you're trying to do some classification problem where you're maximizing the AUC or you're using the AUC for maximization, it might be worth trying to do this loss function for the training, because it's really designed for doing the AUC maximization, right? So you might get slightly better results using this loss function than using the standard logistic loss, or people call it cross entropy loss sometimes.
Right. I mean, I was just wondering, like the speech recognition problems. I mean, it's still classification, but it's more like a lot of classification, right? Like it's not just like one label for item, but so I was just wondering if you tried to sequence sequence.
Okay, so yeah, the question is, have we tried the AUM on the sequence data? And the answer is no, we have not tried it. But do you actually use AUC for evaluation in that context or no?
Yes, not in this context, but like in some of the context.
I see. Well, yeah, maybe we could talk offline about maybe a collaboration where we could try to do that, because if you're using AUC already, there's probably some way to relax it using our technique and get some kind of, maybe not exactly the same thing as what we're doing, but maybe something similar. Yeah. Any other questions?
Je sais
Et-
pas s'il y en a à distance.
Because that's
Le chat. S'il y a des questions à distance, peut-être que vous pouvez lever la main ou les écrire dans le chat le temps que je me repère, je me retrouve comment afficher des trucs dans Zoom. Hop. Non, donc ça va. Donc, s'il y a des questions à distance, c'est maintenant ou jamais pour les poser. Sinon, mais en fait, je sais pas, le truc de. Juste pour être sûr, le truc de line search, tu peux pas le faire si tu changes ton point de
okay, the question c'est sorry, the question is can we do the line search if we change the input feature space?
Yeah, like if you plug it on a neural network. I think you mentioned you can undo it.
Right. Yeah, so the line search that we've implemented, it only works for a linear model. So
Yeah.
if you can compute your, your basic expansion yourself, then yeah, you can get a nonlinear model, right? But if you want to actually learn the neural network parameters, our code is not doing that yet. Like I said, it might be possible to do that with the ReLU. I'm not sure how efficient it would be, but I think it would be piecewise linear to do a neural network learning algorithm directly like this. People don't usually use line search for neural networks though, because I think it doesn't really help that much in terms of speed. So I don't know. I mean, usually people are not even doing grid search, line search in neural networks. So I'm not sure how efficient or interesting it would be. I think interesting from a mathematical perspective, but from a practical perspective, I don't know if it would change how people train their neural networks.
I know there's some results about line search in neural networks, but it's not mainstream. It's not yet empirically superior. So
Yeah.
no one is really using it.
Yeah, actually, Mark Schmidt has some recent work about that. I don't know if you're familiar with his work, but he was studying about how backtracking line search can maybe be beneficial for some kind of training. Yeah.
People don't even do that. Just gradient descent.
Yeah. Yeah, it's gradient descent. It's just with a strange step size. Yeah.
Continuer à discuter offline. Merci.
Ok, merci pour l'invitation. Et merci pour les questions en ligne. Je peux faire ça, les questions à la fin.
Les gens à distance, ça vous dit, bon ben, au revoir tout le monde.